Today, lesson 4A, experimental probability. Yesterday, we started with this idea of probability, and we talked about the very basics of it. We ended the lesson with a quick discussion on theoretical probability and experimental probability. Today, we will talk about both of those again, but our focus will be more on experimental probability. So today you'll be calculating the experimental probability of an event, and we'll use some websites to quickly go through those experiments. If we shoulder partner, you'll be describing what experimental probability is, and then our typical why am I learning this. And I'll stop for about 30 seconds to let everybody get the blank spots filled in there. All right, let's continue on here. A little bit of background knowledge from yesterday. Remember, we talked about sometimes probability is given as a fraction or a decimal, and if that's the case, it's some number between 0 and 1, where 0 is an impossible event, and we defined what that was. And then if the probability is 1, that's a certain event. We also defined what that was yesterday. And then other times, probability is expressed as a percent, or the corresponding numeric values. 0 as a percent is 0%, and 1 as a percent is 100%. So sometimes we also want our probability as a percent. And we defined all of these things yesterday. We talked about what an event was, what an experiment was, what an outcome was, what sample space is, and so on. Probability describes the likelihood that an event will occur. And I defined yesterday what theoretical probability is. That was not in your notes yesterday, but it is in your notes right now. Okay, so theoretical probability, remember, is the number of desirable outcomes over the total number of outcomes. And theoretical probability is what should happen. Doesn't always happen, but that's what we expect to happen. And now I think you have a blank area that you're supposed to fill in. So let's go through a little bit of theoretical probability. So if we have a coin, and we typically call it a standard coin if it has heads on one side and tails on another side. Okay? The event, of course, is flipping a coin. What would the sample space be? And that's from yesterday. What would the sample space be?
Heads and tails.
Heads and tails. So for theoretical probability, remember, it is the number of desirable outcomes over the total number of outcomes. So what do you think the probability is of tossing that standard coin and having it land on heads? Just say it. 50% as a percent. What about a fraction? 1/2. What about as a decimal? 0.5. You know, we've been, the first couple of lessons we're dealing with the fact that those are all equivalent to each other. 50%, 1/2, 0.5. What's the probability of tossing that standard coin and having it land on tails? Just say it. It's 1/2, or 0.5, or 50%. So obviously that's pretty simple. How about this? Probability of tossing that standard coin and having it land on feet? 0. There aren't any feet on a standard coin, so therefore it's 0. Now, this is the most common mistake, is to leave probability if I asked you for a fraction of 0 over 2. That's like having a fraction that's not reduced or simplified. 0 over 2 simplifies to 0, so make sure that you simplify that. So now, let's go to a die or a number cube. Okay, so obviously, and we did talk about this yesterday, we have numbers 1 through 6 on that number cube. The event would be rolling a number cube. Obviously, the sample space would be 1, 2, 3, 4, 5, 6. Remember, theoretical probability is the number of desirable outcomes over the total number of outcomes. So I have some questions for you. First one is, what is the probability of rolling that number cube and having it land on a 3? Raise your hand if you know. Yes?
1/6.
It's 1/6. There's 1 3 out of the 6 numbers on that number cube. So therefore 1 out of 6. What is the probability of rolling that number cube and having it land on an even number?
1/2.
It's 1/2. Now, it starts, one way of thinking about it is there are 3 even numbers out of the 6, but that is a fraction that is not simplified. We always need to simplify fractions no matter what type of problem we're dealing with. Okay? All right, let's continue on with this number cube idea. What is the probability of tossing the number cube and having it land on a 1 or a 6? Well, that's what it would start, right? Go ahead. 1/3. There we go. Yeah, there are two of those 6 numbers are 1 or a 6, and that would be the 1 or the 6 out of the 6, but we need to simplify. And then how about this probability? The probability of tossing the number cube and having it land on a 9.
0.
It's 0. 0 out of 6 is 0. Okay, continuing on. So theoretical probability, remember, is the number of desirable outcomes over the total number of outcomes. We already saw that the probability of tossing a coin, a standard coin, and of it landing on heads would be 1/2, and same thing with tails. Probability of it landing on tails is also 1/2. But do you think if you were to flip a coin 100 times, exactly half of the flips would land on tails? Yes or no?
No.
Maybe, maybe not. We don't really know. Okay? And same thing about it landing exactly, half of them landing on heads. So what we're about to do here is we're about to do an experimental probability, and that's obtained by doing experiments. So to save time, I'm going to use a website that can generate all of them, and I kind of did that a little bit yesterday with the rolling of the dice, where we were adding them together. So experimental probability is obtained by doing experiments, and each experiment is called a trial. We talked about that yesterday. The idea of finding experimental probability is exactly the same as theoretical probability. It's still the number of desirable outcomes over the total number of outcomes. So in your notes, you should have a table that looks something like this. Is that true, yes or no?
Yes.
Okay. So what I'm going to do is I'm going to do a quick flip of 100 times of a specific coin. So we need to wait for this to come up here. And we're going to keep track of everything here. So let me see what I want to do here. Do I want a list or do I want... Maybe I want a ratio. Yeah, there we go. All right. So we're going to toss 100 times, and then from that 100 tosses, you're going to fill in the information in the table. So as you can see from your table, you're going to write the experimental probability, then you're going to write it as a decimal, then as a percent, and then write what the theoretical probability should be for that. All right, here we go. There we go. You know what? I don't like that one. Why? Why don't I like that one? Remember, I asked you guys that question, and you all said no, and I said, well, maybe yes, maybe no. Why don't I like that?
Because it's perfectly easy.
Yeah, and that doesn't happen very often. So let me clear the results, and let's try this again. There, I like that one better. All right, go ahead and fill in that information in your table, and I'll give you about a minute or so to get everything filled in. All right, I have to get off of this screen, so I'll need some of you in case I forget what that just said. How many times did it land on heads? Was that 53?
Yeah.
Okay, so obviously you should be writing 53 over 100, which is 0.53. And that is 53%. Now, what should the theoretical probability be? Just tell me. A half. 50 out of 100 is a half. That's what it should be. That's what we expect it to be. And so if there were 53 heads, obviously there are 47 tails out of 100. That is 0.47. That's 47%. And obviously we expect the theoretical probability to be 1/2. So this is kind of what we're doing today. We're going to do some experimental probability. We're going to fill in some data and then sort of compare what happened here. Now, we weren't too far off, right? 53% is not too far off from 50%. 47% is not too far off. If I kept flipping the coins, we would expect it to get really, really close to that. In fact, I'd like to do that. I'm going to go back to this, and I'm going to flip some more here. I'm going to go like, I don't know how many it'll let me. There's 100,000. Let's see if it'll let me do. Nope. 1,000 is the most I can do. All right. At a time, anyway. So here's 1,000. Let's see how close we get. I'd rather see the ratio. So look at, we're at 51.4% and 48.6. Let me do 1,000 again. And we got even closer to 50%, right? We're at 50.95 and 49.05. So the point is, the more that we toss the coin, the closer we would expect to get to that theoretical probability. And hopefully that makes sense. All right, so let's go to the next thing. Now we have a number cube. We're on the back side of your notes now. Theoretical probability, remember, is the number of desirable outcomes over the total number of outcomes. We found that the probability of rolling a 3 was, of course, 1 out of 6 earlier, and the probability of rolling a 6 is also 1 out of 6. And so I have the same question for you, and that's this. Do you think if we were to toss the number cube 100 times, exactly 1/6 of the tosses would land on a 3? Yes or no? Yeah, maybe, maybe not. We don't know. Same thing about landing on any number for that matter. So now we have another table, and we're going to kind of do the same thing here. We're going to write down the experimental probability, the decimal percent, and the theoretical probability. Let me go ahead and clear this out. And this was the one we did yesterday. So I'm going to do 100 tosses the first time, and then we'll log the data there, and then we'll do it a whole bunch more times. All right, so there we go. Can you see that in the back? Yes?
Shouldn't it be one die?
Oh, yes, yes, yes. Thank you. Let me do this again. 1. Let's try this again. There we go. Okay. If you can't see, landing on a 1 was 17 out of 100. Landing on a 2 was 18 out of 100. Landing on a 3 was 16 out of 100. Landing on a 4 was 21 out of 100. Landing on a 5 was 13 out of 100. And landing on a 6 was 15 out of 100. And I'll let you go ahead and fill in the rest of the areas there. Now, if you kind of look at the expected probability, that's basically what we expect to happen. That's the theoretical probability. So 1/6 as a percent rounded to the nearest hundredth is 16.67%. It's actually 16.6 repeating percent. So, some of them were very close. Like rolling a 1, that was pretty close. Rolling a 3 was pretty close. The other ones weren't too far off. But what if and I don't know how many it's going to let me do. I'll try 10,000. Now look how much closer by rolling another 10,000 times. Look how much closer we got. Rolling a 1, that's 16.91%. In fact, they're all in the 16s. We got really close. Let me just see if I can add another 0 on there. Yep. And look how close we are suddenly getting on all of them. The more that I roll, the closer I'm going to get to the theoretical probability. Okay? All right, continuing on here. I'm not going to worry about filling in the table. I think you get the idea. Let's go now to a spinner problem. On the spinner, we have 5 colors. Blue, yellow, how do you pronounce, is that cyan?
Yeah.
Okay, and then red, and then purple. And cyan, I guess, is the light blue right there. So let's do a little demo here. I know that I have to change the number of colors here. Now that should look identical. And I'm going to spin 100 times. And I would like you to fill in the data. And there it is. We have 5 different colors. Therefore, we would expect the probability to be 1 out of 5 to land on yellow, 1 out of 5 to land on blue, and so on. 1 out of 5 is 20%. A few of them were close, a few of them were not so close. We're going to do a whole bunch more spins here in a second just to prove once again, the more spins we do, the closer we get to the theoretical probability. Okay, so most of us have that filled in. Remember, the theoretical probability is 1 out of 5 because there are 5 colors within that spinner and they're all equally divided up. So let me, I don't know how many I can do. Let me try 1,000 here. So we're trying to see if we get closer to that 1 out of 5 or 20%. You can already see by doing 1,000 we got a lot closer. Let me spin another 1,000 times. And we're getting even closer. Look at 4 of them are 20 point something. It's the purple that's not. But if I keep spinning, I should eventually expect to get close. And we can see we've got a couple that are in the 19s, but one of them is 19.9, which obviously is close, and 19.6 is. So the more we spin, the closer we get to that theoretical probability. Well, that leads us to something that we call the law of large numbers. And the law of large numbers, and this is where you have some areas you need to fill in. It states the more trials you perform in experimental probability, the closer to the theoretical probability you should get. And I just proved it in 3 different situations. A spinner situation, a die or number cube situation, and a coin situation. The more trials you perform in experimental probability, the closer to the theoretical probability you should get. And that should kind of make sense to you at this point. All right, so we're going to continue on with some experimental probability, but we're going to use some strategies that we dealt with in the first couple of lessons. So let's go on here. So the next problem, it says, in the following experiment, a marble is randomly drawn out of a bag and then replaced. The table shows the results after 50 draws. So that means in the 50 draws, 12 times they drew a green marble, 15 times they drew a red marble, and 23 times they drew a yellow marble. And if you add it up, 12 and 15 and 23, that adds up to 50. Find the probability of drawing a green marble as a fraction, a decimal, and a percent. Could I get all of you to do that right now, please? And if there was any question as to why we did the first 2 lessons the way we did them, this is the reason why. So that I don't have to go back now and remind you, oh yeah, that's how you turn a fraction into a decimal, or oh yeah, that's how you turn a fraction into a percent. You should know how to do that. All right, so obviously the fraction is 12 out of 50. Because the number of green marbles drawn was 12 out of the 50 marbles drawn. The event here is picking marbles out of a bag. The sample space is green, red, and yellow. We're supposed to write that as a decimal. Anybody have it as a decimal? That one should be pretty easy. 0.24. And obviously as a percent, that makes it 24%. Okay? 6 out of 25 is 0.24, which is also 24%. All right, continuing on here. And this is a background knowledge from several lessons ago where we would want to create an equivalent fraction. So if we had 4 out of 5 and we wanted to convert that to something out of 20, we did it with modeling, which obviously is the long way of getting there. We should be focusing more on mathematics here. That would be 16 out of 20. Okay? That's what we're about to do, creating equivalent fractions. So let's go back to this idea of marbles, or a marble problem. Back to the previous marble problem. If we assume that each marble color will continue to be drawn out at the same rates, here's a question for you. How many green marbles will you draw if you draw a total of 100 marbles altogether? How many do you think? Remember, we're assuming that we're drawing them out at the same rate. Yes? 24. And the reason is because 12 out of 50 of them were green. If we're now going to draw 100, we're trying to create an equivalent fraction to 12 over 50 that has 100 as the denominator. And that's something that we talked about a few lessons ago. The mathematical way of doing that is multiply top and bottom by 2, and we get 100. Let's continue on here. I mean 24, excuse me. How many green marbles will you draw if you draw a total of 350 marbles altogether? I would like you to figure that out. Okay, I'm going to give you about 30 more seconds, and then I want you to compare what you have for C and D with your shoulder partner. For part C, now we're talking about red marbles. In the original problem, 15 out of 50 drawn were red. We're going to assume that we're drawing them out at the same rate. And so we're trying to find a fraction that is equivalent to 15 over 50 with a denominator of 100. And obviously, to turn 50 into 100, we multiply by 2. So we multiply the top one, the numerator, by 2 as well. So that means there should be 30 red marbles in that situation. And then part D, same situation, but this time how many yellow marbles can we draw if we draw a total of 250 marbles altogether? Yellow, the original, was 23 out of 50. We're assuming we draw them out at the same rate. And so we have a situation like this. We're trying to figure out what that numerator would have to be. So we would have to multiply 50 by 5 to make 250. We multiply that by 5, and that would give us 115 of the yellow marbles. Okay?